for both inviting and introducing. That's very nice. I'm here to talk about classifying sound using machine learning. We will not use animal welfare as an example, but that is a relevant example. And I know people that are working on maybe not the abuse part, but making sure that farms operate well and that you find out when things are not going well. So about me, I'm a specialist in Internet of Things. I have a bachelor's of engineering in electronics from about 10 years ago. But I spend most of my time as a software developer since then, both working on embedded systems, so that's still staying in the electronics land, and also on web. And then I took a master's degree in data science 1 year ago, completed. And now I'm the CTO of Soundsensing, where I try to combine all these skills, into products. So I wrote my thesis on environmental sound classifications on microcontrollers using CONVOLUTIONAL. Very long thing, but basically trying to be able to classify environmental sound in this case, so noise, typically noise from cities, on a edge node. So you can do it directly on a sensor. I forgot to bring my sensor. But it's somewhere around. I will have to just show it. There it is, our sensor unit, which can be battery powered and detect noise. An important thing here is that we don't need to send the sound itself, so the potentially recordings of people or with all the GDPR constraints on, we just do the classification on the sensor node and send the information that we're interested in. Someone stop praying for a second. Send the information that we are interested on, which could be a noise source. So like, okay, here, hopefully the main noise source is the tram or a T-bane, and that we are interested in. So that's what we provide at Soundsensing. We do solutions based on this technology, including, for example, noise monitoring. So you can not only know that, yeah, the noise level here is too high, according to regulations, local or EU-wide, but also understand what is this sound that is causing this problem so that we can do something with it. So this information needs to be actionable. And the goal of this talk is that you as developers, so I'm assuming that you know something about software development, have a little bit of familiarity with machine learning, that you will understand the possibilities and applications of machine learning on audio. So what can we do with this? And the overall workflow of creating a solution that with audio classification. Audio classification is one subtopic of machine learning on audio. And then learn a little bit about what sound sensing, what we provide in this area. So background. Why audio classification? Why are we interested in this? How is it useful? So audio is a rich source of information in general. Like essentially any physical motion creates sound. You can't always hear it, but in many cases you can. And as humans, we use our sound in many ways. We use it for understanding the context, what's around us. Danger, for example, if you're walking near a road and you can't necessarily see the cars behind you, but you can hear them. That's very important. If you work with, say, manufacturing or machinery, good machinists they have usually a very good ear. They can hear, something is not right here. This needs to be looked into. Or sometimes they can even tell you exactly where inside this machine there is a particular problem right now, which needs a lot of training. And the interesting thing with machine learning, and especially with the last couple of years, 5 years or so, we can do near human level performance. So we can, if we have the right data and the right way of modeling the problem, we can implement that expert machinist. And that's very interesting. And also, so there's many applications of this. Of course, audio in general, there's a lot about speech recognition. Of course, we care about sound and communicating with sound with each other. Music analysis. Music is very interesting, and lots of audio machine learning goes in there. But it's also like, let's say, the general sounds. So sounds of a city, sounds of machinery, sounds of maybe people's activities. You don't care to recognize their sounds, but they're making noise, for example. So in ecoacoustics, you use sound to analyze bird migration, to understand, for example, how climate change affects birds, and you need to understand, you need to somehow log the birds, and you can do this with sound. You can do wildlife preservation, where, for example, in an area where you're not allowed to cut down trees, if there are a sound of chainsaws, that's a cause for investigation, right? In quality control in manufacturing, so for example, I know that car seats these days are modern. They have a lot of motors and stuff, and they all need to work. There's like 7 motors in the high-end car seats, and they test them using sound, because you need to test the final product, and you can't really put your testings into or change the car seat. It's already done. You just want to check that it works. So they test it from the outside using sound. That's very powerful. You can do non-invasive monitoring, as it's called. And in medical, doctors, and also this is happening with even some apps these days, you can detect possible heart problems by listening to the heart. And in process industry, there's you can, for example, automate the process. And then there's a coffee machine company here in which I've been working a little bit with prior to Soundsensing, that uses sound to detect when the coffee is properly roasted. They're called röst. Yeah, and the one thing that's also interesting, there's a lot of applications, but we have also a technology landscape. So machine learning is going fast forward, and that's improving rapidly. But we also have, and that's on the, let's say, software modeling and training side, we can do more and more with that. But also the question is, how can we put this into a real life situation? We need this to be done, like not all applications can afford, for example, a full PC with an NVIDIA card and so on running in that scenario. You need a lightweight solution. And then basically all the manufacturing of microcontrollers, they have announced that they will implement in hardware accelerators for neural networks. And that is expected a 10x increase in power efficiency for sensor units like the ones that we provide, which is something, it's another wave that's coming fast. Makes this very interesting. So how do you make an audio machine learning solution? What are the steps? What are the pitfalls? How to approach this? So the overall process, you need to start with problem definition. Of course, you need to think about what problem you want to solve for your user or for your customer. What are the considerations about that? But also you should define it down to, let's say, a task, so that you can, instead of like, oh, we have this animal welfare detection thing, or like what task is that called in the literature, so that you can find, let's say, established solutions for it. You will need to collect data, because unlikely your particular problem has a data set already. You need to label the data, which is quite interesting, often ignored. We'll talk about that. Training setup, this gets more into standard machine learning. It looks very similar to any other, if it's image or text or so on. Feature representation, so we need to worry about how do we model this audio. And we need a model that can do the classification that we're interested in. And then we'll evaluate our solution and deploy into production somehow. So our task, to keep things concrete, we'll talk about noise classification in urban environments. This is what we work on mostly right now, so it's good and concrete, and it's widely researched. So, well, depending on how you search, if you use the term environmental sound classification, you'll get around 1,000 hits on Google Scholar. If you search for noise classification, you'll get near 0. Another important thing, well, just knowing the name gives you superpowers with Google. So I'll give you some names and some terminology along the way. So in 2017, it's estimated on one data set that machine learning models have approximately human level performance on this kind of task. So it's like detecting, okay, is it car noise? Is it children that are playing on the playground that's making the noise? Or is it music on the street? So that's the task. And what we will apply is supervised learning and machine learning. I'm just basic introduction to this. The thing here is that we have a set of sounds in small audio files, for example, and they each have an annotated, so the ground truth or target of what is in this sound with car traffic, speech, so on. And then, okay, you can't really see it, but at the end we want a model, and at the model we can feed in a new sound and get a prediction out of what was it. Was it speech or car or so on? And in this black box is all the magic, the machine learning, that will pop out this model. We will open that box a little bit and see what, because in theory this is how it should work. Like you should just be able to do this, provide data, say what the goal is, and it'll spit out the model. In practice, you need to know a little bit more. So the training process for supervised learning can be seen as something like this. You have your training data, the sounds and the labels, so data and labels. And you need to also have these hyperparameters, which are things that you can't tune. Like, for example, how long of a window of sound do we look at one prediction? That's it's possibly an important question, but the training process can't itself answer it. So we won't talk so much about that part, hyperparameter optimization. It's well covered on the internet in general. We use the data and pre-process it. That we'll talk a little bit about. And then classify, that's our model, like the core of the model. And this makes some prediction, computes some error based on the labels, and the model is adjusted. And this goes around and around, and eventually that classify bit is good enough to be used on your new data. So yeah, classification. So classification, audio classification, that's one task inside machine learning on audio. A classification is that given a sound clip, so it now has a fixed length. It's not infinitely long like a stream of audio could be. With some sounds in it, determine which class these sounds belong to. And there's some important simplifications in classification. We have a single output, so we say like no matter how much sound, there could be any number of sounds going on at the same time, we will have a single output. So we only one class at a time. It's discrete, so the sound either exists, or the speech, for example, either exists in this thing or not. It doesn't estimate how much speech or so on. And it's closed set, and this is an important limitation that people often forget. It must be a known class. So, okay, we have trained it on, let's say, traffic and construction noise, and let's say human noises, so speech and music and so on. These are the three classes. Now, if you put in something else, for example, bird, like some animal noises, it doesn't fit in those three. What will the system do? Unless you make some corrections for it, it will output. It will choose one of those three. Like that's the how you've set it up. So it will make a bad decision because you're feeding it data outside its known set of classes. There are some ways of compensating for that, but this in general you can only predict something that you have predefined. And these simplifications all give limitations to the system. However, they also make it an easier task to deal with, which is why we do them. And audio classification is therefore kind of a base task in audio ML, and other tasks like audio event detection, where you want to be able to know, okay, when exactly did particular sound occur? Like, give me the start and the end of speech, for example. That's usually built on top of classification. And anomaly detection can also be seen as a kind of a where you want to tell them, like, okay, tell me whether this is a new sound. I don't care which sound it is, but it's a new sound or a different sound. You can build on top of classification. So we'll focus in this talk on classification. Okay, so that's our task, and this will already help you on Google. Find my talk on YouTube, at least. But the other important thing is data, right? So we have some idea about our task and the way to approach it, but the other thing is data, and this is a key component. Like, machine learning methods are easily available. You can just download any open source framework, and there's tons of examples. and so on. The important ingredients, which often you don't get for free, is the data that you need. So the key challenge in data collection is ensuring that your data is representative, so that the data that you capture for training is somehow close or on some level identical, very close to what you will be feeding it later. This can be a huge challenge if you have a product that will run on multiple phones, for example. They will all create different, for the same input sound, they will record a different sound. And also if you have a product that is in multiple countries, for example, the noise of sirens in cities, every city has sirens that make noise, but they're very different in different cities because there's probably even regulations about how a police and ambulance should sound in Germany versus Norway versus America and so on. And this, if you don't have that covered, your model will be wrong, and we can almost guarantee you it will not generalize for that. And you need to have enough coverage. So you need to, there's a variation inside your classes and variation between your classes, and you need to cover both of this. Otherwise you will hit this, oh, this is not similar to anything the model has learned. It will make a mistake. Like it will not, it's not, in this way, it's not like a human at all. It will make silly errors all the time. So, and you need to, data collection process is very important to capture the relevant metadata. So you will go out, capture some sounds. Important, like, there are many things that can affect how those sounds work. For example, distance to the source of the sound. The environment around, so you're interested in T-bane sounds. If you only record those at the start and the stop of the T-bane, you will get a T-bane sound, different from the one that just passes in the forest or something. And you should capture all these things so that when you see that, oh, my model does wrong on this, you can use your metadata to understand why is it making this kind of mistakes all the time. Your models also have a tendency to, in general, machine learning, to capture or to base their decision on irrelevant things. So if you would have particular noise on your sensor, for example, and it correlates with a certain class. So like if you used one recording equipment for one sound, the T-bane sounds, and a different recording equipment for speech sound, most likely your classifier will learn to classify what sensor you used, not which sound it was. So many things to be careful about. And that's why you should record in your metadata which device did you use, what type it was, and so on, because then you can uncover these patterns later and correct them. And of course in data collection in general, especially with audio, it's important to maintain privacy. So that's actually like half of our data collection processes is about managing that aspect. So good best practice when you do data collection is think about this thing up front. It's going to take quite a lot of time to collect the relevant data. So think about it up front and write a data management plan for how you're going to deal with this data. That's where you take into consideration how you avoid your privacy problems, for example. And also make sure that you think about metadata and organization, how you'll store it, so that you will have maximum value of your data later. So you didn't spend hundreds of hours of collecting data and missing some important metadata and have to, you have reduced output from your team. So then you should write down a data collection protocol, because you should also be consistent in this process, and you should know, you should have a, let's say, well-defined way of capturing the data, so that you can, and which you will continuously improve as you do. So data requirements. So this is one of the reasons why so many underestimated problems in data and machine learning. One is the quantity. I mean, simply the quantity that you need. So in general, you would want to have 1,000 at least. I mean, this is considered a very small data set these days. 1,000 labeled instances per class. So that in urban sound is 10 classes. It's roughly that size. that's 11 hours of annotated audio. So not just 11 hours of sound, but 11 hours of relevant sound with only the classes of interest that have been labeled. So probably this means that it's collected 10 times, 100 times that amount of sound in order to get to that curated data set with annotated sounds. And but I've seen other cases, or like, for example, with this coffee machine project which I worked on, there we only used less than an hour of sound in total because we had a controlled environment. It was inside a machine that we controlled, sensor environment that we controlled. It was only detecting crack, it's like popcorn cracking, sound versus not. So it's only two classes. And because the controlled environment, the variation within the class, so like each pop sounded relatively similar to another pop. Unlike, for example, if you think about speech, different languages sound different, different people sound different. There are huge amounts of variation. The content, like you talk differently all the time, or you talk about different things. Huge amount of variation inside that class. And then the other question is, how much distance do you have in your classes? So if you have a lot of variation, that's one thing. But if you have two classes with a lot of variation, but they're very close to each other, it's going to be hard to make a distinction. It's going to be hard to make a good choice, like it's this or that. Sometimes you have classes which are overlapping. Like there are like if you have street music and speech, there are things that are street music that also is basically speech. So it's not possible to make a perfect distinction. And yes, that's an important thing here. So data labeling. So this is the act of taking your data, audio in this case, and putting a label on it. In this, we do a classification. We just put, for a certain section of sound, we put this is speech, or this is construction noise, or something like that. The challenge is to keep the quality high and the cost low, because this is usually, or often, this costs a lot of money, because unless you find another really smart way, basically some human needs to go through all this data and label it. That's the human are our reference, and that costs money. So you might need expertise. If you're going to replace that expert machinist, you can't just use people from the street. They won't be able to tell you the right thing. So in that case, you might be paying someone 1,000 kroners per hour to go through your data, right? I might be paying them more. I might be paying them 2,500 per hour. So that it can be very costly, or it will cost. But key questions are like, what is the human level performance? Because you should not expect to exceed human level performance. You might hope to reach that, because it might not be possible to go beyond, or it might in some cases. Humans are not perfect either. But also, if humans are your ground truth, you will have a chicken and egg problem. You can't do better than the person that tells you what's right and wrong. So what is the human level performance? That's something you should evaluate in your labeling process, so you have an idea about what kind of performance can be achieved there at all. If humans can't do it, don't bet your business on that you can do it. That's not a good choice at this point. Also, annotated self-agreement. So if the same person labels the same sound twice, or 3 times, 4 times, 10 times, do they agree? I mean, like, do they agree with themselves? Is there consistency here? This is 2 levels. Like, so if every annotator that you have doesn't agree with themselves, then you have a vague problem, and that's just part of the nature of the problem then. Or how you've defined your classes. Maybe your classes should be more specific, or maybe they are context dependent. So you need to fix it a bit. And that's something you should, if you discover that, you need to correct for it. And the other question is then, like, how do you have inter-annotator agreements? So do 2 or 3 people, different people, agree with each other on what is this label? If you don't have that, it could mean that, again, it might be context dependent, culturally dependent, personal preference dependent, and so on, which you either might be in the nature of the problem. Maybe your users will have the same, let's say, fuzziness variation, or you haven't properly specified or corrected for this. These are the key, like, let's say, ways of estimating how good is our labeling process and our data set. So how to label? You can outsource. There are data labeling services, at least for images. I haven't found any data labeling services for audio, unfortunately. So those are professional. They specialize in labeling, and they manage their own teams and so on, and they ensure that quality is quite high. The other approach is outsourcing, is to take Amazon Mechanical Turk. Just throw this as a task where people can do this for as cheap as possible. Of course, your quality is likely to be different. So you'll have to spend more efforts on quality assurance. Crowdsource, you can try to get the public. If you can make what happens when you solving CAPTCHAs, for example, these days, image CAPTCHAs. You're giving label data to Google as a side result, right? So can you get the public to do it? Can you get your users to do it? In ecoacoustics, I know there's a website where you can label sound, and bird enthusiasts actually go and label sound, and that data set is publicly available. So, in-house, and this question: do you have a data labeling team? Do you put it inside your data science team, and so on? Or can you find some way of automating this? Because it could be very beneficial. So if you can find, for example, another data source, another signal in a sensor system, for example, that tells you whether something is the label that you're interested in, then you might be able to do that for a lot of your things. So there are many annotation tools. We built our own, but based on an open source one called Audio Annotator, a very general name. And it's quite nice. So here you can, I haven't put in a section, but you can mark a section of sound. For example, here in the start, it looks like there's something happening. And there at the end, there's also something happening. Possibly very different sounds because of the way spectrograms look. You listen to that and you mark the region and you put a label on it, and also we let you annotate. Is it a close sound or a far sound or a sound that you're not sure about? And you do that for hundreds, for thousands of cases. And when you've done that, you get a curated data set. So you might have done other steps here too. For example, you might have removed some, if you find that there's some irrelevant data here. For example, when we go out and record, there's a lot of recordings in the start and the end where you hear the sound of someone taking the sensor down. So a lot of handling sounds. Those you don't want in your data set unless that's a relevant thing to detect. So that kind of things. And if you have, at night, if it's near like recording in a T-bane, there's no T-bane at night in Oslo, so probably you want to skip those, or at least skip most of it. You might want to keep a little bit to represent silence or the environment around, but clean that up, and you will decide the classes and end up with something. And then you're let's say done with the first part of the audio. That's where you can think about the model. So often people, if you see things online, including the talk that I did previously, they skip data. Data magically appears. You download it on the internet, and then you use it. I wanted to cover this in this talk, a little bit at least. So how to deal with the audio. So now we're talking about the modeling. I will check the time. Yeah, we have a little time. So we have audio as our input. So this is a audio plotted over time at the top there as a waveform. It's a typical time representation where the sound level increases up and down. And that is, if you have a sensor system, that's theoretically a infinite stream that will go on, until the sun stops. That's not manageable. So we need to cut this up into so-called analysis windows of a fixed size. Basically, almost all machine learning models need fixed-sized inputs. And then we transform this audio into a spectrogram view. So in spectrogram view, you have frequency on the y-axis and time on the x-axis. So we basically have done Fourier transform on like very small sections, and you get this. And that allows you to separate many kinds of sounds. So Low frequency sounds will appear near the bottom. Tones will have a relatively horizontal pattern, and knocks or like percussive sounds will have a pretty vertical alignment. So that in a spectrogram, if you've seen them before, you can often, as a human, you can often see the different sounds. You can see, that's probably speech, or it's probably something else. Like this here is I don't think it's speech, I think it's music, because it has this chord-like pattern, each of those things, but I don't know. But so we do that transformation, and this is great in two ways. It allows us as humans to easily more see the data. It separates many kinds of sounds already and get meaningful patterns. And thirdly, it allows us to use basically image recognition to solve our audio problem. And that's excellent because image recognition is within the last 5 years becomes super good. So you can apply all the latest, let's say, technology and models and principles from image recognition, which is a much bigger field than audio, to your audio problem, to solve your audio problem. So that's a very big advantage of this approach. You can learn directly from the audio. It's being widely researched, some promising results, but I wouldn't call it, let's say, production grade yet in general. So our classifier here is the actual model that we're learning. And then because there's a risk that the label that we had was for a much longer period than 0.72 seconds or some short period, might be even for 5 seconds or so on. So then we need to somehow merge our individual, or we need to map between the label we have for a 5 second period to these individual windows. And the easiest thing is to assume that it was all the same sound inside that and kind of copy it onto each of those. But you need to then merge the results of your prediction, because your prediction will be per these small parts. You need to merge that into one prediction for your 5 second part. And the easiest thing here to do is either majority voting. So if 3 out of 5 was this class, okay, that one wins. Or you can do a mean on the probabilities for each classes. This is also called soft voting, which tends to do a little bit better. Both are fine. Yeah, and then after the voting, so these would be, only shows children playing, but for example, this could be street music, this could be another kind of class, and the highest one wins. So we can use the image model for this, and the standard best performing for that is convolutional neural networks, CNNs. So who here has heard of a CNN or worked with a CNN? Okay, so that's a fair bit. So yeah, they do excellent, and this here is shown a very simple one with 2 layers. Modern CNNs for image classification tasks have 30 layers, 50 layers, 100 layers, and are huge because they often deal with very complex problems, like deciding of 1,000 different categories in ImageNet, for example, of images. Whereas most audio problems, if we exclude speech, deal with much smaller amount of categories. There's an audio set which has defined 631 categories of sound, but most applications that I see, or that at least people have approached us for interested in, are interested in sometimes 1 or 2 sounds, or 10 sounds, or something like that. So, and that means that the models that you use are often quite simple. So you can do, if you have an audio classification problem, start with a really simple CNN. Like start with 2-3 layers and something like that. This model here does, on this urban sound data set, is still near the top of performance. It has 3 convolutional layers and 2 dense layers. So it's a very simple model. And once you have your model and you put it into the training setup that I said before, and that's the same as if it was image classification or it's some sort of text or something. The training loop is the same. So you use your favorite framework, Keras, TensorFlow, PyTorch, whatever. Plug in data in the model, and out comes some results. So here's just shown some results from my thesis with different model variations. So in the thesis, I show that you can reach quite close to the performance of, let's say, the best models that run on PC while still running on a sensor chip. And this gap is going to get closer, like smaller and smaller, especially as we get these coprocessors into the sensors. Okay, summarize. So to summarize on the audio level, wait, there is a, yeah, okay. For classifications, as long as you find a way to formulate your problems, or what you care about in this audio task, as an audio classification problem or audio event detection, there are standard models out there. This pipeline that I showed by splitting into fixed size sound windows, converting to a spectrogram, and then using a CNN will, for many tasks, get you all the way there or nearly. And it's all available as open source solutions, Keras, TensorFlow, and all these things. And my talk on at EuroPython, which is on YouTube, has a bit more details about, let's say, the modeling part. I didn't cover it here since so much other things to cover. Data collection is not magic. Sadly, data collection is something that, for example, online and even in literature and books is not really covered. It's like, well, yeah, you just do something, and then you get a data set, and then you have this data set, and that's great. Or they don't even say that. You just like, oh yeah, you just find a data set. Okay. For some problems, there are large open data sources, but of course, it might not apply directly to your problem, and you have challenges if you try and reuse an open one, where, for example, what if what you are interested in is not well covered? Then you'll have this kind of coverage problems. Or it might just be that for the task, there's no relevant data online. Like no one has that kind of data, or at least willingness to publish it. And also, if you do only an open data, you can't really be much better than your competitors because they all have access to the same models. So data is a competitive advantage as well. So which might be why no one documents how to do this in any detail. But at least I've told you a little bit about what things to think about. Yeah, and it's mostly about structuring your collection up front so that you make sure that you take this task seriously and you budget the required resources both for collecting the data and for labeling the data, and that you integrate quality checking. So you don't assume that, oh yeah, we have labeled data, it must be perfect. It's not. It's an artifact of the process that you set up and let's say the natural world, the natural variation that you have. And both of those are open questions. Like you don't assume that you know that enough about those. Like put some checks. Do people agree with each other on this task? What is the threshold? Like is the expectations of the customer higher than what is humans can do? Then you probably need to talk to your customer and say, this is not the best expectation. And build it up gradually. Start small, do iteration, evaluate, quality, improve, and then so it's doable, but it will take time. And all the clients and people I worked with, this is the big surprise. I don't know why that it takes much longer than you think. It takes 10 times as more effort than you think usually. And yeah. So we went through this process. We have a model that can, that run on our machine and give us some results on our testing set. Says, oh, it does 90% correct, which maybe is not near human level performance. Okay, but we wanted to monitor a real world phenomenon. We wanted something that will work in the barn or something that will work in the streets and so on. How do we deploy this? And that's, yeah, so there's a couple of things here. You need to decide on a strategy for dealing with the data. So one approach would be to send all the sound from your sensor to the cloud, to the server, and then do the classification there. Then you can use exactly the same model that you have trained on your PC and tested already. However, you will now, or depending on the environment that the sound is captured, this might be okay privacy-wise, or it might be completely not okay privacy-wise. Even it could be legal challenges with that. So that's that. But if you have a room where you know there are no humans, this might be an acceptable approach. It still is. It's also data transmission-wise the most. The one that requires the most energy. So that will limit your ability to put your sensor on battery and so on. But it might be okay in some circumstances. You can do the spectrogram conversion on the sensor and send the spectrograms over. This will at least compress your data quite a bit. Depending on how you structure your spectrogram, if it's very high resolution, you can actually invert this into sound again, so you have still privacy considerations. But there's some research showing that if your spectrogram is sufficiently coarse-grained, it's not possible to recover the speech anymore. So you can't hear what people are saying. So then you're doing better for privacy. Audio embeddings, I haven't talked about it, so I won't, but there's a way to compress a learned representation using a CNN, for example, of say 1 second of sound, and you can get just a point in a space. So it's hard you can't understand it as a human anymore, but it has somehow the relevant information. So it's possible to do. That's research level stuff so far. Or you can move the entire classification onto the sensor and only send out the, let's say, the decision or the prediction that was made. That is the one that costs the least in terms of data transmission. However, it does cost more in data processing on your sensor. But this balance generally is in favor of, or can often be in favor of, lower power usage. And especially with neural network accelerators, that balance will shift dramatically. So that's our kind of, and with sound sensing, we can use a combination. We can do this part, and we can also do a spectrogram with low resolution to avoid privacy issues. So if we look at our kind of our platform, we have applications at the top, so who might be using certain solutions. We are right now working a lot on noise monitoring, so giving acousticians, but also people in the construction industry or offices, information about what noise is going on. And you have models there that can be reused. We're building some of those. What we're focused on so far is a lot on this sensor and data transport. So we provide a sensor, and it transports the data to database, and you can just access that in an API. So that if you know machine learning and HTTP APIs, you don't have to deal with all the, let's say, IoT sensor data transport parts. We will handle it for you. And then we will also provide more of the models up there eventually. And other applications that people are approaching us about is, for example, condition monitoring. So understanding how machines are doing in manufacturing or real estate, ventilation systems and so on, or process industry. So yeah, that's what we provide. And then yeah, we can deploy models. Either we can have models running in the cloud, or we can have them running directly on the sensor device. So here's an example of that. Not so including. So it's classifying in real time, and here's children playing. It's now the main one. The bar there represents this kind of a threshold. So if everything is below that bar, say, I don't know, rather than say, oh, it must be this thing. There's drilling, it's a little bit. Construction type noise. And all the classification is running on the device. So it's just reporting the predictions over USB. Dog barking. I think this one is interesting because that doesn't get picked up. The woo. There was like two different components to the sirens. The first part, the doo-doo-doo-doo, didn't pick up. The second one did. So somehow that part was probably, I haven't checked this data set that we used to train this model, but it's quite likely that that type of siren sound was not represented in that data set. So the model didn't know. It didn't know that this could be a siren. And yeah, and all these things what we put together to build this noise monitoring solution for acquisitions, and we are running pilot projects with customers now. Okay, as an outro, we have some calls to actions for you guys. We are building a kind of partner network. So we see that in many cases, customers want something really specific, and we would like to keep, our small focus. We are a small team, 3 people in the core, and a bigger, like around 10 people that are around. We need to keep those at, let's say, on the generic part. So we're interested in partners that are interested in delivering solutions and integrations for particular needs. So the customer says, "Oh, I want this kind of thing," so that someone can help us with that. So Knowit, and it's quite could be interesting for that. So reach out to me later or by email if that's interesting to you. We are also hiring. We have some internships running in data science now. We still have maybe a spot to there, and we're hiring 2 developers in 2020. So if you think this sounds cool and interesting, then get in touch with me. And we're also fundraising right now. As a startup does, you kind of have to, right? Well, you both have to to be called a startup, but also because we still need some money to fund projects. We're funding round open now. You can talk to Ola, who's sitting there, and we have quite a lot of commitments already, but we still have some open slots. So
it's closing in now, so it's actually more like 80% commitment.
Okay, so be fast.
So if you have some money burning in your pockets.
Yes, get in touch. Yeah, I have quite a lot of resources on machine hearing and machine learning on audio online. I put as much as I can out there because it's compared to image, text, and so on. It's a smaller field, yes, and it means there's less learning resources. It's a bit harder to get started. So I try to put as much. So these are links you can go to learn a bit more. And my thesis is also available online. So, questions? Yeah.
So, in your sample,
we should use the microphone. Yes.
Yeah. I know. So in your examples, you use very, in my opinion, like simple sound samples, right? That played like it was one major sound that was distinct. This is children playing, or this is a car horn.
Yep.
But are there neural networks or solutions to complex soundscapes? So in everyday city life, as an example,
yep.
I walk down the streets and I can hear children playing, I can hear a dog barking, a car going by, and a siren.
Yep.
Right. And for automotive vehicles and such, understanding sound as like a sound,
yep.
like a sound radar would be interesting, right?
Yes.
Is there a solution for this?
Yes, our solution, I don't know, but there's a whole research field and many application. So you would typically model them as a multi-label classification or a tagging task, so often called tagging. Then you will get a, let's say, percentage of probability. It's not the percentage of, so at least for multiple. So you can have like, oh, there's this thing and a little bit of that thing. So reforming as a label task, there's a challenge at DCase, which is a small but significant conference in this area that has that particular use case as this automotive context understanding. So there are a bunch of open source implementations and papers describing their approaches, and it seems to be doing pretty well there. Also in this data set that we have here, there are also sounds that are far in the background. It's still just annotated with one sound, but there are definitely tricky ones, and that's why humans even can't get to the top. It's like, hey, there's some sound there, it could be, and then it's in 5 seconds, 10 or 4 second intervals, so often sometimes you can't precisely determine what it is. So definitely there are, you can go that far, and things are moving that direction. More questions?
So you say as there's a lot of research on image using images or cameras for classification, but not as much on audio. Do you think audio classification can match the performance of image classification?
Yeah, I mean, it is, so image classification reached, these estimates, but reached kind of human level performance around like 5 years ago or so. And audio, depending on the time, I mean, it's not always, like for example, in speech, we're not near human level yet. And we have been trying since the 70s to get there. And so it's been a big bump with the deep learning, but still not, so, but many practical tasks, it seems that, yeah, we are at close to human level performance on audio tasks. But like speech and music understanding is really, can be really complex, what people expect.
Thanks.
More questions? Yeah. Way back.
Throw it.
Nice.
Thanks. Have you tried to use more than one microphone to do classification?
I haven't personally tried that, but this is a lot of research. Actually, that's a good point. It's another, let's say, technology wave. So for example, an Alexa now has 8 or 16 microphones in an array, and it can actually use multiple microphones to, you can both do classification with all these microphones, but also you can actually get a cone of sound. So if you have noise source there and this interesting thing there, you can actually focus to a level that sound in that direction, and then you run your classification on that. And again, the DCase conference has, I think now 2 years in a row, a case where they have microphone arrays, I think 5 of them in a home, and like each have 16 sensors or something like that. So that's definitely very active research, and it's gonna, yeah, it's gonna be in home or like in challenging applications, like for example automotive as well. I'm almost willing to bet that they are not looking at single microphone solutions. They are looking at clusters of arrays, so like 8 microphones here, 16 microphones there, because they're so cheap these days. So yeah, there's lots. There's methods specifically for that, and then beamforming is this concept where you get a single channel audio from a multi-channel array of sensors.
Thanks.
More questions? There's one down there and one here.
So that makes me wonder about another area of research, which is using multiple microphones for triangulation or like precise direction and speed vector measurement, if there's any research, if you know about any research and the status of that.
There I have found less, but we are very, very, very interested in that because it fits our sensor network model very well. So there are some approaches, but we have actually one pilot project where that's very relevant, and we actually for that one we will have a master's thesis. I hope. I mean, because I haven't seen enough research on this. Next spring is planned. So if anyone's interested in researching that, come talk to us, and then we can.
Wouldn't that be more sort of traditional DSP work?
It's a question where you put your, let's say, put the boundaries. So say we have maybe outdoors or a room like this. We have a couple of sensors in different locations, and we're interested in here knowing not just there was speech here, but where there was speech from. Then you can split this into, let's say, one part that does finding, that does the triangulation and so on in a DSP technique. This has been studied for a long time. Yeah. You can do that, and then you do classification. Or you can treat this as a joint task, where you give a network or 2 networks working together. You say, learn, please, both localization and classification at the same time, because there's information from the local thing that helps you, but also information from the classification. So the speech has a certain, let's say, register and might have certain propagation patterns in space, because it's certain tones and so on, and that might reflect more or less and so on. So there's information. If you know that it's speech, you can do better on localization. If you know where it is, you can do better on the classification. So jointly training that should be, and there is research showing that it is possible to get higher. So that's the research motivation for that.
Just a comment. I know that in 2011 there was a company working on a sniper positioning system that uses both beamforming and triangulation for detecting snipers.
Yep.
And yeah, it's a Kongsberg-based firm, so you could
Okay.
Google it.
If they're still around,
Yeah.
then
I'm not sure if they still operate.
if they're not, there might be some research that we can find. There's also something called Shot Spotter in the US, and some cities have this deployment where they localize gun sounds in a urban environment.
Yeah.
At least they say they can do it.
And I have another question. Have you looked into doing classification on the frequencies that we can't hear?
No, not me, but for example, eco-ecology bats are beyond our hearable range, so that's researched quite a lot there. So I'm not sure what the status is, but I don't see, like, it's probably, I mean, it's probably not very different from the thing. Actually, I was contacted by someone interested in radar as well, which is really high frequencies in the gigahertz range. And they said that, yeah, we think that audio type approaches can work here. They have also a spectrogram, which has a very different frequency range, but still shows patterns in the time frequency domain. And sonar, I guess, is also something that in military applications probably is being researched. Any more questions, or are we done? Okay, we're done. Thank you.
Yeah. Thank you, Jon.